Hello, welcome to another module of this course, Microwave Integrated Circuits. This will be our last module in this course. It will primarily deal with oscillator design. So, oscillators are special class of circuits in any field, whether in microwave frequencies or at lower frequencies, in that they are autonomous systems. Whereas while discussing amplifier design, we had seen that there is an input and an output. In an oscillator, there is no input as such. There is only an output. So we saw from a discussion on stability that for a system to be stable, for a bounded input, it should produce a bounded output. But then, as I mentioned, when we are talking about oscillators, it produces an output without any input. So it is a fundamentally unstable system. At the same time, it has to produce a constant, it has to produce an output of constant amplitude, or at least the amplitude we should be able to control. So it cannot either, the amplitude cannot go down to 0, neither can it explode. So there is an aspect of stability also involved in oscillator design. So all those things we shall discuss in this module. So the first thing is to discuss about oscillators. We need to go back to our feedback model. So recall that diagram that I had used. Here everything is the same except instead of a negative sign here, it's all positive here. So the signal, the feedback signal is being positively added to the input signal, and so this is a frequency selective network. This is our gain block. This is an input voltage. For now, let us assume that the input voltage is a noise. So this is what we call a feedback oscillator system. In this system, even if there is no input, or if there is just a disturbance at the beginning, then an output V out will be produced, which is self-sustaining. An alternate way from the circuit point of view, from the reflection coefficient point of view can also be given for this oscillator. Suppose you have an input network like this. Suppose there is a small noise voltage Et, this is the noise voltage, and suppose we have an active device like this. This is a resonator. Suppose this is the incident wave in this direction, and this is the AL is my incident wave in the opposite direction. Then the signal flow graph diagram for this circuit will be something like this. This signal flow graph diagram I am drawing from the discussions that we had many modules ago. So once we draw this signal flow graph diagram, what happens is that at the point of oscillation, what happens at the point of oscillation? At the point of oscillation, this Zin, which is primarily a function of the amplitude of oscillation, should be equal and opposite or negative of the impedance offered by the resonator. Now, in terms of the reflection coefficients, we can show that this condition can also, actually I should have put omega 0, Zin is also, might also be a function of omega 0, that is the frequency of oscillation. Now, here this A0 and omega 0 are the amplitude and frequency of oscillation. So, this is the amplitude and frequency at the oscillation point, where there is a, where this condition or this condition is satisfied. Now, proceeding from the model that I had drawn previously, this model, you know, right, that V out over V in can also be written as AV upon 1 minus AV beta. Now, V out is produced, if for V out be produced even when V in is 0. So, for that to happen, we should have 1 minus AV beta is equal to 0. This in turn implies AV beta should be equal to 1. This condition, let me use a fresh page for this. This condition that, you know, this AV beta is equal to 1 is also known as the Barkhausen criterion. So, this in turn means, if we go back to, you know, if we go back to that feedback diagram, it means that the total phase change over this entire feedback path should be 0 or 360 degree, and the total gain starting from this point all the way through to the other end and then back should be 1. Okay. So, this gain is also known as by the term called loop gain, that is, loop gain should be equal to 1 and the loop total phase change over the loop should be equal to 0 or 360 degree. Now, proceeding with this definition, let us see what else we can find. So, first we saw that our Z in, which is a function of omega A0 and omega 0, should be equal and opposite to ZL, and this in turn can be further reduced to 1. But note one thing, that this condition is applicable only at the point of oscillation. Now, at the point of oscillation, no input need to be provided to this feedback system. But for it to start oscillation, that is, for the amplitude to grow from its 0 value, the system has to be fundamentally unstable. So, at the start of oscillation, we have to have an instability. How do we introduce that instability? So, for this we go back to the condition for stability that we had studied earlier. That is, that at the start of oscillation, our modulus of R in omega A, note that here I am not using the terms omega 0 and A0, because this is at the start, not at the steady state, should be greater than RL of omega. Okay. So, here R in is the real part of my Z in and RL is the resonator part. Now, so, this is my ZL. Now, here we are assuming that this oscillators can be divided into two parts. one which is strongly dependent, whose value is strongly dependent on the amplitude and to a lesser extent on the frequency, and another purely frequency dependent part ZL. Now it can be shown, so the oscillation has started and say the point of oscillation has been reached. At the point of oscillation, however, in order to ensure stability, there is a condition called Kurokawa's condition, which states that beta if this condition is satisfied, here note this R in and X in are the real and imaginary parts of Z in, XL and RL and XL are the real and imaginary parts of Z in. If this condition is satisfied, then we can safely say that the oscillation is stable. That is, the oscillation will continue at a constant amplitude. Now graphically, this is shown in here. This blue graph is a plot of ZL. This plane is the Z plane, that is the y-axis is the imaginary value of Z and the x-axis is the real value of Z. This blue curve represents the variation of ZL with frequency, and this red curve represents the variation of Z in minus Z in with amplitude. Now the points where these two meet, that is the points where ZL is equal to minus Z in A, are the potential oscillation points. But then there is no guarantee that even though they are potential oscillation points, we are not sure whether they are stable oscillation points or not. So the condition for oscillation was given by that equation which I showed previously. But then what does it mean graphically? What it means graphically is that if the angle between the two lines, suppose with increasing A, the red curve is moving like this, and with increasing omega, the blue curve moves like this, then the angle between the tangents to the two curves at the point of intersection, okay, suppose I draw a tangent here and a tangent to this blue line, the angle between the two will determine whether the oscillation is stable or not. If the angle between the tangents of the two curves at the point of intersection is less than 180 degree, then the oscillation is stable. If the angle is greater than 180 degree, then the oscillation is unstable. So for example, for this particular point, you see that the angle between the red line and the blue line, the angle by the way has to be between the minus, the first, it has to start from the tangent of the minus Z in A curve and end in the tangent of the ZL curve. So in this case, the angle is lesser than 180 degree. Therefore, this point represents a stable oscillation point. In this case also, the point of oscillation, at the point of oscillation, the angle between the tangent of this minus Z in A curve is and the tangent to the ZL curve is lesser than 180 degree. Therefore, this point also represents a point of stable oscillation. However, at this point, as you can see, the angle between the red line and the blue line, that is the tangents to the red line and the blue line, is greater than 180 degree. Therefore, this point does not represent a stable point of oscillation. This is an unstable. Either the amplitude will blow up, become very large, or it will die down. So, how do we design an oscillator? So, to design it, you have your transistor. If your transistor is this, then at the point of oscillation, you should have this gamma L multiplied by gamma in should be equal to 1. So, what you can do is, suppose we assume that your transistor has its own termination network which produces a given gamma in. Then all you have to do is simply make an input matching network which has an input reflection coefficient gamma L such that gamma L multiplied by gamma in is unity. Of course, here you have to first start the oscillation. So, here suppose you assume your resonator, this resonator to be a simple series RLC network. Then gamma L will be given like this. Okay, if you just a simple Laplace transform of the input impedance of this Laplace. This is this expression for the reflection coefficient is obtained from ZL, which can be simply calculated. And this, at the point of oscillation, you have to have your R in A modulus of R in greater than RL. Now, after some mathematical manipulation, you can be shown that condition reduces to this. So, your input, the RL of the resonator should be such that it satisfies this condition. So, in summary, oscillators as I mentioned, are a little different from the other amplifier circuits that we have studied so far, in that they have no inputs, only outputs. By inputs, I mean no AC input. There can be DC inputs, of course, but no AC input. And their design is a bit different from that of amplifiers in the sense that there is no gain involved, gain term involved, or linearity term involved. Oscillators, first of all, they need to be started. So, for starting, they need to be unstable at the startup of oscillation, and by this example of a series resonator, I just gave you an idea of how you can design your resonator so that the oscillator circuit is unstable at the startup. That is the first one. And also at the point of that is first part. First, the startup of oscillation is the first important. The second important thing is that it should have a stable oscillating point. That is, there should be a point where this minus Z in A curve meets the ZL curve. That is the second point. And third, this point where these two curves meet should also be stable according to the Kurokawa theory. The Kurokawa theory, which I gave by this equation, if you could shift to by this equation, reduces to a graphical form like this. If you could shift to the curve on the monitor, please. This curve. So, that equation which I showed previously reduces to this. It can be shown that equation is equivalent to this graphical analysis, where the intersection point, the angle between the two tangents of the two lines at the point of intersection should be lesser than 180 degrees. So, I hope so. This is we have come now to the end of this course. This was the last topic of this course, and I hope you like this course. There will be an exam as per the schedule given on the web page. I hope many of you take that exam and do well in it. Please join the forum and ask me any questions. I try to participate as much as I can. In case I am not in case you do not reach me in the forum, please send me an email to my email ID. Also, you can talk with the PAs, they are always. And thank you for participating in this course, and I hope you found some fruitful information from this course, and you will be able to use this knowledge in your future endeavors. Thank you.